Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 16, Straight Line Regression Part 4. So in this chapter, we've talked about several different things. Today, we're going to talk about interpreting the test for the slope and the intercept and what it means. Last time, we talked about how to actually do inference about the slope and intercept. And we gave confidence interval formulas for both, and we gave hypothesis tests for both. So we should be able to perform confidence intervals or calculate those and perform the hypothesis test at this point. So now let's talk about what it means, what these tests actually mean. We're going to start with the slope. When we test for the slope, most of the time, our hypothesis statement is that the slope is equal to 0. If the slope is equal to 0, then basically we have y is equal to beta naught plus e left, which is a constant. That's the same as just a line at beta naught, okay? So this is the most important test when we're doing straight line regression, is the slope, because it determines whether or not we have a linear relationship or just a constant relationship. For if this is not rejected, then, and we're assuming that we don't have any type 2 error here, that we're making the wrong decision, then if it's not rejected, then for a true underlying straight line model, we're saying that X doesn't provide much, if any, help in predicting Y. And in other words, Y bar is just as good at predicting Y as is our equation here. Y bar plus beta 1 hat times X bar, X minus X bar. So basically, let's say y bar is 10, then if I want to predict the value of y at 0, then I would say 10. If I assume that I don't reject beta naught or beta 1 equals 0, if my null hypothesis is not rejected, then if I want to predict the value of y at x equals 0, it's going to be the value of y bar. And the same thing at 1, it'll be y bar, 10. And at 2, y bar, 10. At any value that's in the range of the data, I would just say y bar is my value. Okay? That's the predicted value. If we don't reject the null hypothesis that beta 1 is equal to 0. So if the slope can be set at 0, then we use y bar as our predictor of y for every value of x. So that's the first possibility. The second possibility is that the true underlying relationship between x and y is not a straight line. It could be a quadratic or a cubic or square root, etc. So here's a quadratic case where we have the full quadratic, so we end up plotting a flat line using the least squares method for a straight line. The straight line that best fits this is a flat line with 0 slope. Now, I showed more of the square root than I probably should. If you saw this, you'd end up with a straight line, something like this, which would not be a slope of 0. But what I was trying to show here is that if you keep on, a square root flattens out. So that if you were, let's say, in this zone, and you had values just between the blue lines, you would be very close to fitting this with a straight flat line with 0 slope. So that's another possibility. Depending on what range you're in and how much of the curve you capture in your data, that will determine whether or not you think it's a straight line or not. So we have two possibilities. If beta naught equals 0 is not rejected as a null hypothesis, then either x is not a very good predictor of y or doesn't contribute to predicting it, and we just use y bar, or we have some other relationship between x and y that's not a straight line. Okay. Now, if we do reject the null hypothesis that beta 1 is equal to 0, then assuming we don't have any type 1 error, again, we didn't make a mistake here, then X does provide significant information for predicting Y. In other words, the model that we come up with, and I keep forgetting the hat there, Y bar plus beta 1 hat times X minus X bar is far better than our naive, what we call the naive model of just using Y bar for predicting Y. So if we reject H naught beta 1 equals 0, then we're saying that the first possibility is that X does provide significant information for predicting Y when it's a straight line situation like this. However, it still could be that a better model may exist, even if we find it significant. So here, my blue is not working very well. Let me change this to red. Maybe it'll show up better. I could plot a straight line through this, and it might be significant. And the slope is not equal to 0, statistically, let's say. But this data would still be better fit with a cubic than with a straight line. So even if that's one of the reasons that we need to look at a scatter plot to make sure that the shape that we're seeing is a straight line shape or not. Because even if it's statistically significant, in this case, we should not use a straight line to estimate this. We should use a cubic. We should fit the best model that we can, and we'll learn how to do that later. Now, the test for the slope, that was the test for the slope. For the intercept, we're going to test beta naught equals 0. And this tests whether or not the line passes through the origin. So do we have a line passing through the origin? It can be a different slope, but still passing through the origin. Okay. If we do not reject the null, it still may be appropriate to remove the intercept from the model, because we're saying that it's 0. It may still be appropriate to remove it from the model if our theory suggests that it does go through the origin, and we can take additional observations near the origin to verify this. So if we do reject this, then we would definitely leave the intercept in the model unless we are, again, positive that it does go through the origin, or it should. And even though maybe it should, if we are, let's say here is 0, and we're taking data way out here, well, here it may be that if we extended this line, it doesn't go through the origin, and maybe it should. But with our data, we're only going to make predictions in this range. So we would not remove beta naught from this equation, even if the theoretical situation says it really does go through the origin, because it's significant and we're way out here and we don't have any data near the origin. So I hope that helps explain what these tests mean and give you a little insight into what we should do here. Okay, make sure you scan your lecture notes by midnight of the date listed on the course calendar. Again, these are yours, so you're your own customer. Be neat. I didn't really do anything with the formula sheet, so nothing really to update today with that. If you have questions, please come for virtual office hours. If none of those work for me, then email me. When you email me, take a picture of the problem, take a picture of your work, send it to me, ask me a specific question. I'll be glad to help you. We will see you next time.